Okay, let's unpack this. We are usually deep diving into the bleeding edge of electrification, the 800-volt architectures, the exotic silicon carbide inverters, all that hypercar stuff pushing for 500-mile ranges. But today, our mission is, well, it's entirely different, and I would argue far more strategic for the future of global mass mobility.
Precisely. We are shifting focus dramatically. We're moving from that high-performance EV market, which is defined by luxury and range, to the gritty, cost-driven, volume reality of the micro-low-speed electric vehicle, the LSEV segment.
Right.
This market is where billions of units will eventually sell. It's the real revolution.
We're talking about the vehicles that are truly defining urban transport right now, especially in Asia and Europe. You've got to name check the stars here. The Chinese juggernaut, the Wuling Hongguang Mini EV, which just sells in staggering volume.
Unbelievable volumes.
Then you have the ubiquitous European urban solution, the Citroën Ami, or even Japan's really successful cost-optimized Nissan Sakura.
And these models, they all define the segment, and their engineering success really hinges on a critical conflict. If we're advising an OEM entering this space, we have to solve that conflict strategically, not just, technically.
And that conflict, as we've discussed internally, it's this extreme, ruthless push for cost efficiency. I mean, every single penny shaved off the bill of materials.
Every pen.
And that slams headlong into the need for robust, globally compliant safety, all while you're trying to cram enough usable energy density into a minuscule physical space. It's the ultimate trilemma of cost, safety, and packaging.
It is, and that's why our goal today, as we tackle this deep dive, is to execute a classic consulting mission. We are acting as the chief systems engineers for a major automotive consultancy. We are building the foundational, detailed engineering requirement specification, the SOR, for an LSEV battery management system from the ground up.
So this isn't just a technical checklist.
Not at all. This SOR has to be a strategic value document. It has to dictate everything, from the specific components we source to the global markets the vehicle can actually access.
We have to transform these highly technical parameters into real strategic business value.
And we have to recognize that the regulatory environment is not sitting still. It's not waiting for us. Our strategic analysis already shows that global LSEV voltage architectures are converging, and they're converging rapidly on a very specific economic sweet spot, the 96 volts to 144 volts range. And more critically, the strict new Chinese GB 38031 2025 safety standard is fundamentally changing what safe means, even for the cheapest, most volume-driven vehicles on the road.
Okay, so that's where we have to start, the regulatory minefield.
For an LSEV BMS that's targeting global scale, the first step is completely non-negotiable. We have to establish the engineering boundaries based on these mandatory global safety standards. The BMS, it's not just a battery manager, it is the gatekeeper of compliance.
Right. If the BMS can't certify the pack safety, the vehicle simply cannot ship. End of story.
Exactly. These are the mandatory shell requirements that we have to define for our engineering team immediately.
And globally, it seems like we have to start where the volume and the strictness are highest, which is China. Let's lead with that zero-tolerance benchmark, the new GB 38031 2025 standard. You mentioned it's more than just an update. It sounds revolutionary in its demands.
It is, and that's not an exaggeration. It is the most severe, most demanding battery safety mandate globally today. It's replacing the previous 2020 version, and its implications for battery packaging, for chemistry, and specifically for BMS software are profound.
Okay.
We have to look at the critical shift in the thermal runaway requirements. This is really the heart of the standard.
The old standard, the 2020 version, that was focused on passenger safety, right? It just required a 5-minute warning before a catastrophic thermal runaway so that the occupants had time to escape. It was about delay.
Exactly. The 5-minute rule was an escape window. It was a delay tactic. The new 2025 standard mandates something entirely different and, frankly, far more difficult to engineer. It requires that after a single-cell thermal runaway event is triggered, the entire battery system must prevent fire or explosion for a minimum of 2 hours.
2 hours. That's an exponential leap. That's not a delay. That's demanding indefinite thermal containment and structural integrity.
It forces a massive philosophical shift in design. The SOR has to demand that the battery pack is not merely designed to delay a catastrophe for 5 minutes, but it's designed to contain the thermal event for 120 minutes.
Wow.
And this fundamentally impacts everything, from the fire retardant materials you use in the casing to the spacing between the cells, and most crucially for us, the BMS's role in predicting and mitigating the event before it becomes widespread.
Okay, so that requirement immediately forces a complete redesign of the BMS software strategy. You can't just rely on passive fuses and, high-level temperature monitoring anymore.
That's the strategic impact right there. The SOR has to shift the requirement from passive monitoring to highly active predictive diagnostics and containment. The BMS can't simply cut the main contactors and walk away, declaring an error.
That's just not enough anymore.
It's completely insufficient under this new rule. It has to actively manage the situation. This means the BMS software must integrate advanced thermal diffusion models. It needs to be running algorithms to predict how heat will spread from a hotspot. And it has to be capable of executing active control strategies.
And in this cost-driven segment, that active control usually translates to one thing: active air cooling. The BMS has to orchestrate a fan system.
Precisely. And beyond just control, the monitoring has to be sharper. It has to detect the incipient failure seconds before you see any smoke or fire. To achieve this, we need multi-sensor fusion.
Okay.
The BMS must integrate data not just from standard slow-reacting temperature sensors, but also from pressure sensors that are strategically placed within the battery enclosure.
Pressure sensors. Why pressure sensors?
To detect the microventing phenomenon, this is the rapid release of small quantities of electrolyte vapor and gas, which occurs moments, literally seconds before the cell casing fully breaches and goes into full thermal runaway.
So it's the earliest possible warning sign.
It's the earliest non-optical warning signal we have. Detecting that microventing through a subtle pressure change is key. So the BMS detection logic for fusing these pressure and temperature inputs is a non-negotiable requirement in our SOR.
And the regulatory scope extends beyond that, right? It goes into data logging and remote monitoring, which adds a lot of complexity to a low-cost MCU.
Absolutely. GB 38031-2025 mandates robust remote monitoring under the GBT 32960 standard. This means the BMS microcontroller has to have enough computing power, and specifically the communication bandwidth, to transmit crucial real-time data.
What kind of data?
Individual cell voltages, temperature gradients across the pack, insulation resistance status, fault codes. And this data has to go first to the vehicle terminal, the TVOX or the VCU, and then be uploaded in real time to the National Monitoring Platform.
I see. It's for traceability and regulatory oversight.
Exactly. And requires a much more powerful and reliable communication stack than just simple internal CAN messaging.
Okay, shifting gears, let's move west to Europe. They use a dual safety architecture: ECE R100 and the more specific R136. What's the fundamental difference in focus here?
Europe strategically recognizes the physical and functional difference between a full passenger car, an M-class vehicle, and a light quadricycle, an L-class.
Right.
R100 is mandatory for the former. It focuses on common safety elements like thermal propagation limits, high dielectric strength, and general vibration. It mandates that a single cell failure does not spread across the pack, which is similar to the core principle of the Chinese standard, though without that rigorous 2-hour requirement.
So a lot of LSEV makers will comply with the R100 anyway.
Yes, many LSEV OEMs comply voluntarily, even if they only need L-class certs, simply to boost product perception and market trust in the quality of their battery system.
But R136 is the one that's specific to the L6E and L7E categories. We're talking vehicles like the Citroën Ami. What makes R136's focus on mechanical integrity so different?
What's genuinely fascinating from an engineering standpoint is that R136 actually demands a higher tolerance for specific mechanical shock and random vibration profiles than R100 does.
So, hang on. Why would a lower speed vehicle need stronger physical packaging? That seems counterintuitive.
It does, but the answer lies in the chassis design. LSEVs, to save cost and weight, frequently lack the complex, multi-link, robust suspension systems of a full-size car. They often use rigid axles or minimal suspension travel, sometimes just basic leaf springs or simple struts.
Ah, so the high G road inputs potholes, speed bumps, uneven surfaces. They're transmitted much more aggressively and directly into the battery pack structure itself.
Exactly. The battery pack is essentially acting as a structural member that's subject to severe shock loading. The strategic impact on our BMS SOR is clear. The PCB design must be rigorously verified against stricter, higher-frequency random vibration profiles than typical automotive components.
And what does that mean in practice?
It means we have to specify component mounting techniques, maybe using specialized epoxy staking or low-density underfills for large components, and mandatory conformal coating across the entire board to prevent moisture ingress and mechanical fatigue failures.
And the connection points, they become the real failure points under that constant microvibration.
They do. Connectors need high-grade locking mechanisms and perhaps even redundant retention features to prevent fretting corrosion.
Fretting corrosion.
It's a silent killer in high-vibration environments. It's where constant micro-movement between contact surfaces leads to oxidation, increased resistance, and eventually localized overheating or signal loss.
Got it.
And furthermore, insulation monitoring is crucial under these rough operating conditions. Our SRR must mandate maintaining greater than 100 ohms per volt of insulation resistance across all expected operating and vibration conditions.
Okay, finally, let's turn to the USA with the focus on crash safety and integrity under FMVSS 305A. This is all about post-collision safety.
FMVSS 305A, which harmonizes with Global Technical Regulation number 20, focuses intensely on limiting electrolyte leakage and, most importantly for the BMS, preventing electrical shock.
And there's a hard number there, isn't there?
There is. The hard deterministic engineering requirement is that the high-voltage bus voltage must drop below 60 volts DC within seconds after a collision is detected by the vehicle's safety system.
That requires immediate, irreversible action from the BMS. So how do we ensure that deterministic rapid shutdown when the entire vehicle system might be compromised in a crash?
There's a classic redundancy problem. Our SR must mandate a dedicated hardwired crash signal input.
Not just a CAN message.
Absolutely not. A CAN bus can be compromised, delayed, or fail entirely during a severe collision. A physical hardwired signal is required for redundancy and speed. It has to come directly from the airbag control module, the ACM.
So a simple voltage transition?
Exactly. Upon receiving this signal, the BMS must execute a deterministic emergency shutdown, triggering pyrotechnic fuses or forcibly opening the main contactors. No questions asked.
And the timing of this action is critical.
It is. The response time has to be minimal, often under 100 milliseconds, but crucially, that exact response speed and the operational state of the contactors must be logged. We require integration with the event data recorder, the EDR.
Ah, so you have a black box with a battery.
That's right. The EDR logging requirement ensures that we can validate, post-accident, that the BMS safety function performed correctly under duress. It provides both legal and engineering accountability.
That regulatory minefield sets the constraints. Now, before we design a single physical component, we have to lock down the voltage platform. This decision is fundamental. It influences the entire cost structure, efficiency, component availability, and crucially, charging compatibility.
This is the core strategic trade-off that defines the LSEV segment. We are navigating the choice between the legacy 48-volt systems and the emerging 96-volt to 144-volt range.
Let's start with the attraction of 48 volts. Legacy low-speed vehicles loved it because they use dirt-cheap commodity MOSFETs, and critically, they sidestep all the complex regulatory hurdles that kick in the moment you cross 60 volts DC.
Right.
No need for HVIL, no mandatory IMD. That's a huge cost saver up front.
That's the initial seduction of 48 volts.
Right.
But physics quickly defeats it. For a typical 20 kilowatt motor output, if you operate at 48 V nominal, you're pulling hundreds of amps, 400, 500 amps, easily. The power loss due to resistance scales with the square of that current, the I squared R term. You suffer massive, unacceptable resistive power losses throughout the harness and the inverter.
And to combat that loss, you need to use massive cables.
Precisely. You are forced to use heavy, thick, and expensive copper wire harnesses. In a vehicle where every kilogram and every dollar of copper counts, the cost penalty and weight gain of these large harnesses at 48 volts completely erode the savings gained from avoiding those HV safety features.
Which brings us to the golden zone. The strategic path modern LSEV leaders are pursuing. 96 to 144 volts. But I have to challenge you as the chief systems engineer. You are willingly jumping over that 60-volt threshold. You are forcing the design team to implement HVIL and IMD major cost adders. How do you justify that immediate regulatory and hardware hurdle for a cost-driven vehicle?
That's a critical question, and it's justified by looking at the total system cost, not just the component cost. By moving from 48 volts up to 96 volts, we're roughly halving the required current for the same power output.
Okay.
Having the current allows us to dramatically reduce the wire harness cross-section. This translates directly to significant savings in copper cost and weight savings that immediately outweigh the cost of implementing the mandatory IMD and HVL systems.
So we trade cheap wires for cheap power electronics.
More accurately, we trade expensive thick copper harnesses and massive I-squared-R losses for slightly more complex but still highly cost-optimized silicon. This 96 to 144 volt range allows us to use commodity, widely available industrial 150 to 200 volt rated silicon-based MOSFETs.
And that's the strategic crux.
It is. We are deliberately avoiding the exponentially higher cost of the 650-volt or 1200-volt IGBTs or the cutting-edge 6 devices that are mandatory for 400 or 800-volt architectures. We are utilizing the cheapest, highest volume silicon components available globally.
And what about the safety trade-off itself? I mean, protecting a 96-volt system versus a 400-volt system, the physics are on our side.
Absolutely. While we must introduce HVIL and IMD, the protection required for a 96-volt system is significantly less complex and more controllable than what's needed for 400 or 800 volts. The physics of arcing at 96 volts are much, much friendlier.
Right.
High voltage transients and severe arcing hazards are a massive design consideration at 400 volts, requiring thick insulation and complex isolation barriers.
Yeah.
At 96 volts, the risk is contained with comparatively simple measures.
Let's look at the implementation. The Wuling Mini EV is the poster child for this low-voltage strategy.
It is the perfect example of cost optimization. Whirling utilizes a nominal 96-volt architecture, typically built with 30 to 32 series LFP cells. By locking into that voltage zone, they successfully utilized 150-volt silicon-based MOSFETs and standard capacitors in their inverter and other high-current systems.
And it works.
It works perfectly. This architecture efficiently supports their urban ranges, from the basic 9.3 kilowatt Rapri up to the larger 26 kilowatt pack.
Yeah.
It demonstrates that 96 volts provides the best trade-off between efficiency and component cost for a power output typically under 30 kilowatt.
Then you have Toyota moving slightly higher with the C+ pod at 177.6 volts. Why the slightly higher bump if 96 volts is the ultimate cost sweet spot?
That's a key strategic difference between players. Toyota chose a higher 177.6-volt system not primarily for absolute cost minimization, but to maximize driving efficiency and regenerative braking capability.
Okay.
Crucially, they did this to leverage their existing extremely mature high-voltage component supply chain, which was originally developed for their world-leading hybrid electric vehicles. Their strategy is supply chain leverage and component commonality rather than absolute BEBO minimization.
So for our client who's focused purely on LSEV, the guidance must be strict to hit that defined cost target.
Absolutely. We must mandate a nominal voltage range of 96 to 115 volts, which translates exactly to 30 to 36 series LFP cells. This ensures optimization around that 150-volt commodity MOSFET supply.
And there are other benefits.
Yes. A critical secondary benefit. At this voltage, the PCB creepage and clearance requirements are significantly less stringent than for 400 or 800 volts, which allows us to miniaturize the BMS board and reduce the stack-up cost.
Okay, moving into the hardware layer. We have to emphasize that for LSEV, every decision is cost-driven, but never at the expense of that regulatory safety. The choice of BMS topology defines a massive chunk of the bill of materials.
And its reliability. And for this compact, low-voltage 96-volt segment, simplicity dictates that centralized topology is king.
That's right. For battery packs under 100 volts and with a manageable cell count, say 36 cells or fewer, the centralized topology provides the best cost and reliability proposition.
Definitionally, it means all functions, voltage sampling, temperature sensing, control logic, contactors, and current sensing, are all integrated onto a single main PCB board. Cell connections run via a direct harness to this board.
Why does this beat the modular or master-slave architectures we see in premium EVs, which are often cited as being safer or easier to manage?
The cost logic is just irrefutable here. A centralized design eliminates the need for multiple expensive slave boards. It eliminates dozens of interboard connectors, which are high-cost, high-failure rate components in a high-vibration environment. And crucially, it eliminates the expensive isolation transceivers like dedicated CAN or other isolated communications chips that are required for master-slave communication. For a 96-volt pack, we only need to daisy-chain 2 or 3 analog front-end chips via an isolated protocol like ISO-SBI directly onto that single main PCB. It drastically reduces the boom complexity.
When would we ever deviate? When would we allow the engineering team to consider a semi-distributed approach?
Only under severe physical constraints. If the vehicle design requires the battery pack to be physically split, say, half under the driver's seat and half out of the passenger area, the sheer length and cost of running the high-voltage sampling harnesses back to a single centralized board might outweigh the cost of adding a very simple single-slave board.
But for a standard single-box pack design?
Centralized wins. It reduces part count and potential communication failure points.
Okay, let's detail the critical components in our SOR, starting with the brains of the system, the microcontroller, the MCU. We need an MCU that balances low cost with the computational horsepower needed for complex state-of-charge algorithms and all those safety checks.
Functional safety is the primary constraint. The MCU must be rated for or capable of being used in a system targeting, ISO 26262 ASIL B or C.
And strategically, we need a dual supply chain approach for risk mitigation.
For sure. For high-volume export models where traceability is key, we specify established automotive-grade suppliers like NXP S32K or TIC 2000. These offer features like lockstep cores, where two processing units run the same code simultaneously and compare results, and hardware security modules for robust fault detection.
But the LSEV mandate requires extreme cost focus, especially for that domestic Chinese volume.
Exactly. For that extreme cost optimization, we specify competitive, high-volume domestic suppliers. You think GigaDevice with their GD32 line based on Cortex M23 or M33 architectures, or MindMotion with their MM32? These chips are not only significantly cheaper, but are also AEC Q100 certified.
Wait, let's pause there for a moment. AEC Q100 certification. For the listener, why is that certification crucial, and what does it actually guarantee?
That's a great question, as that term is often thrown around without context. AEC Q100 is the stress test qualification for packaged integrated circuits in the automotive environment. It guarantees that the chip can reliably operate over the specified temperature range, often -40 to 125 degrees Celsius, and withstand automotive stresses like temperature cycling, moisture, and electrical transients.
So that's a mark of durability.
It is. For our SOR, mandating AEC Q100 ensures we aren't using industrial or consumer-grade chips that will fail prematurely under engine compartment heat or battery vibration.
Okay, back to the SOR specification for the MCU.
We mandate a 32-bit architecture, a minimum of 128 KB flash, support for CAN-FD communication, which is faster and more robust than classic CAN, and critically, dual analog-to-digital converters, dual ADCs.
Why is that dual ADC requirement so important?
It's a vital safety layer. It allows the BMS to simultaneously measure the main current using two separate channels. If one ADC fails, the other provides redundancy, preventing a situation where the BMS loses awareness of potentially dangerous overcurrent events.
Next up, the analog front end, or AFE, the cell monitoring IC. This is the precision tool, and precision is notoriously difficult with LFP chemistry.
The AFE's precision is paramount because of LFP's extremely flat open-circuit voltage curve. I mean, imagine trying to differentiate between 40% and 60% state of charge when the voltage only shifts from, say, 3.25 to 3.28 volts.
It's almost impossible.
This flatness makes voltage-only estimation unreliable. So, to achieve accurate SOC correction based on periodic OCV measurements, our SOR must demand an AFE with voltage measurement accuracy of plus or minus 1.5 millivolts or better. If we can't hit that precision, our state of charge prediction will drift wildly.
And on the physical side, how do we connect these AFEs across the centralized board?
Isolated daisy chain communication is mandatory. This includes technologies like NXP's TPL or ADI's ISO SPI. These methods allow us to connect the chips in a serial chain, minimizing the number of expensive isolation components like optocouplers, simplifying the PCB layout, and reducing EMI risks.
For cell balancing, which keeps the cells aging evenly, the LSEV standard is passive balancing. What does our SOR specify here?
Passive balancing uses resistive heating to bleed excess charge from higher voltage cells. It's the LSEV standard solely because of its low cost and simplicity, despite its significant drawbacks.
It's slow and inefficient.
Very. The SOR must specify a balancing current capacity, typically 100 to 300 milliamps. And we have to acknowledge its limitations. It's slow and it generates waste heat. To manage that heat, the AFE must include integrated thermal throttling, automatically limiting the balancing current if the local PCB temperature gets too high.
So we mandate passive overactive balancing purely on cost.
We have to. The complexity and cost of inductor-based active systems violate the core LSEV cost mandate.
Moving to current sensing. The choice between Hall sensors and shunt resistors is a major cost point.
For this segment, the shunt resistor is strongly recommended. It is a simple resistive component offering superior intrinsic accuracy, extremely low temperature drift, and a far lower BOM cost profile compared to Hall effect sensors.
And it has to be paired with something, right?
It must be paired with a high-precision isolated delta sigma modulator.
Explain the modulator. Why is the delta sigma type critical for this application?
The delta sigma modulator, like a TI AMC 3305, is essential because it is designed to measure very small voltage drops across the shunt resistor, often in the millivolt range, in the presence of high voltage noise. It digitizes the signal with extremely high resolution while rejecting noise, giving us a clean, high-fidelity measurement of current.
Which is fundamental for accurate Coulomb counting.
Absolutely.
Yeah.
And we actively avoid Hall effect sensors. Unless absolute galvanic isolation is a non-negotiable safety mandate, which it isn't, due to the low voltage, then yes. Hall sensors introduce zero-point drift and magnetic hysteresis, which complicate long-term SoC accuracy and drive up cost.
Okay, finally, the mandatory safety interlocks, starting with the high-voltage interlock, HVIL.
HVIL is the simplest physical safety measure. It's a low-voltage sensing loop that runs through every single high-voltage connector in the vehicle. If any connector loosens, the circuit opens.
And the SOR has to define the response.
The SRR must define a rapid response. The BMS must detect that open circuit and command the main contactors to cut power in less than 50 milliseconds. This timing is critical to prevent dangerous arcing.
And the insulation monitoring device, or IMD, required because we exceeded 60 volts?
Essential. The BMS must actively inject a signal to measure the leakage resistance between the high-voltage bus and the vehicle chassis. This detects physical breaches in insulation that could lead to shock or fire.
What are the thresholds?
Our contractual thresholds must be clear. A warning must be logged and displayed at 500 ohms per volt, and a hard fault that triggers immediate contactor opening must occur at 100 ohms per volt.
We talked about cost optimization for the IMD. Dedicated modules are expensive. How do we keep the cost down?
We use a strategic component choice. The SOR can specify a software-implemented IMD solution rather than using an expensive dedicated hardware module. This typically uses an MCU-controlled resistor bridge circuit.
But the verification must be robust.
Extremely robust. But if successful, this technique saves hundreds of dollars per unit, which is massive in the LSEV BOM.
We've established the hardware floor. Now software. This is where we enable high safety performance at a low hardware cost through intelligent design, and the core starting point is functional safety strategy.
The top-level safety objective, preventing a catastrophic failure like an overcharged fire, is typically classified as ASIL-D. The crucial hurdle is that pursuing full ASIL-D compliance through hardware alone, meaning using only D-rated components, is economically impossible for LSEVs.
So we adopt this strategic shortcut, functional safety decomposition.
Absolutely. We decompose the high safety goal, ASIL-D, into two separate redundant paths, where each path requires only a lower rating, typically ASIL-B. This is the strategic justification for using those cheaper, high-volume MCUs.
Let's break that down with an analogy.
Think of it this way. ASIL-D requires having a main brain that is infallible. Since infallibility is expensive, we build two separate fallible ASIL-B systems that act independently.
So we have the primary path, the main brain, and the secondary path, which acts as the independent guardian.
Exactly. The primary path ASIL-B is the main MCU and the AFE chips. They handle all the complex tasks: measurement, sophisticated SoC calculation, and primary contactor control. The secondary path, also ASIL-B, is the independent guardian. It uses a very simple single-purpose protection IC or a tiny auxiliary MCU.
And it only monitors the most critical parameters.
Yes, extremes of voltage and temperature limits, that's it. And its action is totally separate from the main brain.
Crucially, yes.
If the guardian detects a critical fault, say severe overvoltage, it does not send a CAN message to the main MCU. Its singular hardwired function is to directly interrupt the contactor coil power. It physically overrides the main system.
So even if the main MCU locks up or the software crashes,
The secondary guardian still opens the high voltage connection.
this strategic practice allows us to achieve the system-level safety target of ASIL-D while utilizing those cost-optimized but lower-rated MCUs. It's a brilliant way to satisfy both cost and regulation simultaneously.
It's mandatory for LSEV viability. Now let's tackle the software challenge for LFP, state of charge estimation. We mentioned the flat OCV curve earlier.
Right, it's the biggest headache for the software team. That curve is virtually horizontal between 20% and 80% SoC. A purely voltage-based estimate is unreliable for the driver.
Therefore, the algorithm requirement in our SOR is stringent. The BMS must use Coulomb counting, tracking every electron in and out as the base. But Coulomb counting, while excellent in the short term, always suffers from cumulative measurement error or drift.
Think of Coulomb counting like your car's odometer. It accurately tracks distance, but if the initial calibration was slightly off, the error compounds over time.
That's a perfect analogy. To stabilize that drift, the Coulomb counting must be constantly corrected by an extended Kalman filter, an EKF.
Okay.
The The EKF is a probabilistic algorithm that runs a sophisticated internal model of the battery, taking in noisy current and voltage data and subtly correcting the cumulative error based on the known physics and usage profile. It acts like a GPS, constantly checking and refining that odometer reading.
But even the EKF needs a hard reference point, a reset button for cumulative error.
That is the OCV static reset logic, and it is the crucial correction mechanism for LFP. The software must be able to recognize relaxation points. This is when the vehicle has been switched off and the battery is completely static with no current draw, typically for 2 hours.
Because the OCV voltage, while flat during discharge, is highly accurate when the cell is at rest.
Exactly. The BMS software uses that single, highly stable OCV reading to reset the cumulative error of the Coulomb counting. This logic is absolutely critical for maintaining long-term accuracy, and our SR must target a maximum cumulative SOC error of less than 5% over the vehicle's lifespan.
So without that reset, the range gauge would be useless after a few months.
Wildly inaccurate.
Right.
Beyond current charge, we need to track the battery's health over time. State of health, or SOH. SOH monitoring must primarily track the increase in direct current internal resistance, or DCIR, over the life cycle. As a battery ages, its internal resistance goes up, meaning it can deliver less power and generates more heat.
And that's what the driver feels.
Exactly. The driver cares more about power loss than capacity loss in an urban car. By monitoring the rise in DCIR, we can predict the effective end-of-life point.
Finally, defining the safety actions in case of a critical event fault management.
The SOR must clearly define the requirements for limp-home mode. This is a strategic intermediate state. If a fault is detected, like localized overheating, the BMS must strategically reduce performance, say, cutting the maximum allowable peak current by 50% to get the vehicle to safety.
Rather than just shutting down and stranding the customer.
Exactly. We also need contactor welding or sintering detection logic. When a high current is cut, the contact points can sometimes fuse or weld shut. The BMS has to run a diagnostic check to confirm the contactors have physically opened after the command to do so. If they've welded shut, it needs to trigger a backup.
Okay, that makes sense. Let's move on to thermal management.
LSEV thermal management is, as we noted, the art of minimalism. We have to achieve mandatory thermal consistency and safety under that new GB 3080031-2025 rule, but we are severely constrained by physical space and cost.
That immediately rules out liquid cooling, which is standard on most 400-volt vehicles.
Liquid cooling is too heavy, too expensive, and requires far too many auxiliary components, pumps, chillers, valves, complex tubing, which drive up the beam cost massively. Our strategic choice for the SOR must be active air cooling.
Why not just passive air cooling?
It's simply too risky. It inevitably leads to localized hotspots inside the pack, causing inconsistent cell aging and premature capacity loss, which violates our product longevity goals.
So active air cooling a blower fan controlled by the BMS. What specific metric defines the success of this system in the SOR?
Thermal consistency is the KPI. The BMS must control fan speed using a sophisticated PWM output, basing its decision not just on the highest cell temperature, but critically on the temperature difference, the delta T, within the pack.
And what's the goal?
The contractual goal must be a cell-to-cell temperature difference of less than 5 degrees Celsius.
5 degrees Celsius difference across the entire pack. Why is maintaining such a small delta so important, especially for LFP?
Because temperature is the single biggest driver of cell aging and degradation. If one cell is consistently 10 degrees hotter than its neighbor, it will age faster, lose capacity faster, and create a significant state of health imbalance across the series chain.
And that just accelerates the problem.
It does. This tight delta T target is also critical for adhering to the non-propagation rule of R100 and GB 38031. A thermally uniform pack is a stable pack.
Now, let's address LFP's famous Achilles heel, charging in cold weather.
This is a major safety and longevity concern. If LFP batteries are charged below 0 degrees Celsius, they undergo irreversible damage known as lithium plating.
Right.
Lithium ions plate out as metallic lithium on the anode surface, leading to permanent capacity loss and, over time, dendrite formation that can cause internal short circuits and fires.
So the BMS must implement a mandatory low-temperature heating strategy.
The SOR must include the control logic for a PTC, a positive temperature coefficient heating film, or PAD, installed directly in the battery pack structure. The protection logic is paramount. When the pack temperature drops below a safe threshold, typically 5 degrees Celsius, the BMS must instantaneously prohibit cell charging.
And divert the power to the heater.
Exactly. It commands the onboard charger to divert the incoming charging current to the heating element until the battery pack returns to a safe operating range, usually around 10 or 15 degrees Celsius. This priority for heating over charging is non-negotiable for longevity.
This brings us to the biggest challenge for global market viability. The 96-volt charging conundrum when dealing with public DC fast charging infrastructure.
This is not a technical problem, it is a market access problem. Standard public DC fast chargers, whether using CCS2 in Europe and the US, GBT in China, or Jordamo in Japan, are all designed for 400 or 800 volt architectures.
They have a minimum voltage?
Yes. They have a minimum output voltage typically starting around 200 volts. A 96-volt battery simply cannot connect to and be charged by a charger that starts at 200 volts.
The physics of voltage matching create a brick wall. If we ignore this, our LSEV is locked out of every major public fast charging network.
Exactly. You are confined to slow AC charging or proprietary home charging solutions, severely limiting the vehicle's utility for urban users who rely on public infrastructure.
So what's the solution?
If fast charging is required for market acceptance, which it is for any export model, the BMS SOR must specify a communication protocol to coordinate with an onboard boost converter.
This boost converter is effectively a dedicated DC to DC circuit designed to actively raise the battery voltage.
Yes, it takes the 96-volt input and boosts it, perhaps temporarily up to 200 volts or higher, just enough to handshake and initiate charging with the public charger's minimum connection threshold. The BMS manages this voltage matching process via precise CAN communication, ensuring a seamless and safe connection.
And for cost efficiency, we hope this boost converter isn't a totally dedicated, expensive box.
The most strategic, cost-effective solutions use patented technology to integrate the boost circuitry into the existing traction system. For instance, leveraging the motor windings or the traction inverter power electronics to perform the boost function when the vehicle is stationary and charging.
Ah, so you avoid a dedicated, expensive, high-power unit.
Exactly. The SOR must ensure the BMS logic is built to manage this integrated boost process from the initial design phase.
And for standard AC charging, which is the most common use case for these urban cars globally.
The SOR must define robust support for standard 3.3 kilowatt onboard charger communication protocols. This involves processing the J1772 or Type 2 control pilot and proximity pilot signals. Most crucially, the BMS must issue the real-time maximum charge current limit, or CCL command, via the CAN bus.
And that limit is dynamic.
It has to be. It changes based on cell temperature, current state of health, and cell voltage, protecting the battery from overstress during the charging cycle.
We've now completed the strategic analysis, defined the architecture, and selected the necessary hardware and software algorithms. The final step is transforming all of this into the ultimate deliverable, a detailed contractual engineering requirement specification ready for an RFQ to a Tier 1 supplier.
This implementation phase is all about supply chain leverage. Our success as consultants hinges on finding and utilizing mature, Tier 2 suppliers who specialize in high-volume, cost-optimized solutions, rather than attempting to develop every complex component internally. That's just too costly and too slow for LSEV timelines.
Which system integrators should the RFQ target, particularly given the centralized expertise in China for LFP cost optimization?
For BMS system integrators, we look for scale and specific LFP experience. Octillion Power is a critical target. They are a key willing supplier and possess deep expertise in cost-optimized LFP battery pack assembly and BMS integration.
Okay.
Tritech, or their European subsidiary Helbuco, are strong contenders for light EVs and offer valuable experience with European export compliance standards like R136.
And what about the big players like BYD?
While we respect large players like BYD FinDreams for full powertrain integration, relying on them presents a competitive supply chain risk, so they serve more as a benchmark for performance and cost for us.
And the semiconductor strategy needs to be clearly articulated to our suppliers to manage risk and regional cost variances.
Exactly. The chip strategy must explicitly mandate the dual path we identified. We require NXP or TI for the AFE chips and for the MCU in export compliance models, where that ASIL safety traceability is paramount. But for the core MCU and high-volume domestic models, we must include cost-optimized suppliers like GigaDevice or MindMotion in the RFQ.
So you can swap based on cost or supply chain shocks.
Exactly, without having to fundamentally redesign the entire ASIL decomposition architecture.
Let's finalize the contract now. You need to summarize the non-negotiable points that must be included in the RFQ. This is the commanding contractual language of the SOR.
These are the 7 pillars that define the project and must be included in the contract.
First, regulatory compliance.
Mandatory compliance with GB 38830 in 2025, specifically the 2-hour thermal containment, zero heat propagation requirement. Additionally, meeting ECE R136 for enhanced L vehicle vibration resistance and achieving the system-level ASIL CD safety target through ASIL decomposition.
Second, architecture and voltage.
Centralized topology is mandatory for BOM cost optimization. The nominal voltage must be locked into the 96 to 115 volt LFP range to maximize efficiency gains while utilizing commodity 150 volt silicon components.
Third, electrical requirements.
The system must use shunt-based low-side current sampling with a delta sigma modulator, ensuring a full temperature error of less than 1%. Active insulation monitoring is required, with a hard fault threshold set strictly at 100 ohms per volt. And the HV-hour response must be rapid, less than 50 milliseconds.
Fourth, software and algorithms.
SOC estimation must be EKF-corrected Coulomb counting, explicitly integrating OCV static reset logic at defined relaxation points to maintain long-term accuracy. And SOH must be tracked via DCIR monitoring.
Fifth, thermal management.
Mandatory PWM fan control for active air cooling, aiming for a critical cell delta T of less than 5 degrees Celsius. And essential low-temperature protection via PTC heater control to prevent lithium plating below 5 degrees Celsius.
Sixth, charging and interoperability.
This is the critical market access solution. The BMS must include mandatory logic for communicating and coordinating with an onboard boost converter to achieve DC fast charge compatibility with high-voltage public standards like CCS2 and GBT.
And finally, validation.
The RFQ must demand a detailed design verification plan, a DVP, encompassing stringent requirements like random vibration testing to the ISO 16753L vehicle profile and fully documented short-circuit endurance testing. These specifications transition the project from the concept phase into mass production readiness.
Okay, so if we synthesize this entire strategic exercise, what's the primary takeaway?
The takeaway is clear. The development of the LSEV BMS is no longer the simple cost race it might have been 5 years ago. The regulatory environment, particularly the seismic shift introduced by GB 38031-2025, has forced a level of complexity predictive safety algorithms, active thermal control, robust multi-sensor data logging that was previously reserved only for premium 400 and 800 volt EVs.
The entry price for genuine safety in the mass market has dramatically increased. The bar has been raised for the entry-level vehicle, ensuring that even the cheapest urban EV is now robustly protected.
For any new engineering team, the path to success is defined by strategic integration efficiency. Locking in that 96 to 115 volt platform and the centralized topology is the single best way to optimize the bottom cost without violating these strict safety rules.
But there's a catch.
There is. The charging issue, that 96 volt incompatibility with public infrastructure, must be solved upstream in the powertrain design phase.
The boost charging strategy, or the integration of that boosting function, must be a mandatory requirement baked into the powertrain design from day one. Otherwise, that vehicle, no matter how cheap or safe, will be locked out of the critical public charging infrastructure market, severely limiting its viability and sales potential.
This entire exercise proves that the cost of safety is rapidly converging across all vehicle segments, from the cheapest microcar to the most luxurious sedan.
Which leaves us with the final provocative thought for you, the listener, to mull over. If LSEV safety requirements now technically mandate systems that mirror the complexity of premium EVs, requiring ASIL decomposed, actively cooled, multi-sensor BMS systems, what does this convergence mean for the future cost and availability of even the simplest urban electric vehicles? How long can the cost differential between the cheapest 96-volt system and the most advanced 800-volt system truly last before the mandatory safety features eat up all the savings?